Hola, amigos tensores. Hello, tensor friends. I got a really good question here. And I remember when I was first studying the covariant derivative, I asked myself the exact same question. And it has to do with how the basis vectors are treated when you take the covariant derivative of an actual vector, not just the component, because you normally see the covariant derivative written as that of the component. What if you take the covariant derivative of the whole vector? So that's what the question has to do with. And it's a good question because it's not obvious. Okay, when you took the vector, the calculus, and you would take the derivative of a vector in Cartesian, the coordinates. So you have a vector written as a linear combination of its components and basis of the vectors. So that would be it would have an x component, a y component, a z component, and it would have the three basis vectors ex, ey, ez. You may have called these x hat, y hat, z hat. Okay? So when you take the partial derivative of that vector with respect to an arbitrary the coordinate, so we put it in as its linear combination here. Now this is a product, so we had to do the product rule. So the first times derivative of the second plus the second times derivative of the first. Okay? Now, what is this? The partial derivative of a basis vector with respect to a coordinate. Well, these basis vectors are orthonormal vectors. They're constants. So what's the derivative of a constant? 0. So this term drops out completely in Cartesian, the coordinates, and you're left with this expression, which is what you're used to seeing, right? The derivative of a vector with respect to a coordinate is equal to the partial derivative of its components with respect to that coordinate times the basis vectors. That's what you normally are used to seeing in vector calculus. Now, what about the case where the basis vectors are not constants, as they are in curvilinear coordinates? They're not constants, okay? They change all over the space. All right, so we could write the covariant derivative of that vector and express the vector as a linear combination of its components and basis of vectors, right? Now look at this. We only got one free index in this whole equation, which is j. So it always has to remain in that position. This is a product, so we take the product rule, first times derivative of the second, plus the second times derivative of the first, all right? Now let's break this out by itself and expand it, right? So we're taking the covariant derivative of a covariant object. So the first thing we always do is write down the partial derivative of that with respect to the coordinate j. And since it's in the covariant position, we put a negative, and then we add our connection. So you need one connection for every index on this, whatever this is, okay? And you see here that we've got our free index in the right place, our free index in the right place. So this is the summation index, and here's the summation index. Okay, so now, if you've been doing this for a while, which you probably have, or you wouldn't watch the videos that I make, you instantly recognize that, right? That is the definition of the Christoffel, the symbol, right? So the derivative of a vector is a vector, and it can be expressed as a linear combination of its components and basis of vectors, okay? Now we have two free indexes, I and j, here they are, and this is our summation index. So let's put this right back in there, and we get this expression, and they're the same thing. So they're equally opposite. So the answer is the covariant derivative of a basis vector is equal to 0. So this entire term here drops out. This becomes 0. So you're just left with this, and it usually looks like this. Okay? So you're used to seeing the covariant derivative of a vector component is equal to this. But the covariant derivative of the entire vector, you have to add in the basis of vectors, as we did. Now, the fact that you can just take this outside of the parenthesis, you see, it's just, you can put it over here, you can put it over here, left or right, doesn't matter. That is called the metronyllic property. The metronyllic property. All right. For the same reason the covariant derivative of the metric tensor is zero, it's for the exact same reason. Let's look at the tensor, and what is it? So we have the covariant derivative of the metric tensor Gij. What is the metric tensor? Well, it's the inner product of the basis of vectors. Once again, we have a product, so we do the product rule. First times derivative of the second plus the second times derivative of the first. Well, we just showed what this is, right? This is zero, and that's zero. So the whole thing is zero. So the covariant derivative of the metric tensor is also zero for the same reasons we just showed above. All right. This property, the metronomic property of the base of the tensor, is part of the fundamental theorem of Riemannian geometry. It says that what this means is that as you parallel transport the metric tensor around your manifold, the inner product is remaining the same and the angle between the two basis vectors remaining the same. So that's what it means. Okay? I hope that answered your question. Let me know.